Today, we want to look at the unit circle again, but this time not just in degrees, but we want to break it down using radians. Now, we like degrees because a full circle is 360 degrees. And 360 is an awesome number because it's divisible by so many things. Divide it in 4, by 2, by 4, by 6, by 8. Super useful. So many divided. Good number. 5-star, wouldn't use it. But it's not very good as for our sinusoidal functions. When we start wanting to look at how things change over time, when we want our inputs not to always just be angles in degrees, but real numbers. We want to apply trig functions to real numbers, and for that, we need to use radians. Radians are kind of annoying because one full circle, instead of being this awesome 360 degrees, divisible by so many things, one full circle is 2 pi radians. It's not rational. And it's also not rational that instead of just being pi of one full circle, 2 pi is 1. So annoying. Anyway, let's just start breaking this down and look for the patterns and how we can associate the angles that we already know, 30, 45, and 60 in all 4 quadrants, with their equivalent values in, or their equivalent measures in radians. We're going to start with 360 is 2 pi. That's one full circle is 360 degrees. One full circle is 2 pi radians. 360 degrees is 2 pi. We normally don't write radians. We see the pi and we just think, all right, it's radians. If it's degrees, we'll write the degree symbol, but for just radians, we don't write anything. It ends up starting to look like toilet paper in supermarkets, where you have like mega rolls where 12 is equal to 36. And then in the next one's over, it's like the super mega rolls and 12 is equal to 48. Like, what kind of math is this? Incidentally, that's marketing math, which is completely different. It follows an entirely different set of rules than radians. We're just going to start breaking up this 2 pi in the same way we break up the 360. It's going to lead to fractions. So if you're like all anti-fraction, you are a fraction hater. Today's going to be a lot of fractions. I just want to warn you. Fractions are coming. Everybody okay? They're just fractions. Fractions are number 2. Don't be all numerical racist. So we're going to start with 360 is equal to 2 pi. And we're just going to break these down by fractions. So if we cut this in half, we get one of our most important ones. Cut this in half, and we get 180 is equal to pi. 180 degrees is equal to pi radians. Just divide everything by 2. We think 2 divided by 2 is just a 1. There it is. Visually, here's 1 pi, 2 pi. 1 pi, 2 pi. Let's take the positive wins where we can get them. If we're counting by 180 degrees, we're counting by pi radians. So if we start off here with 0, here's 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, 8 pi. We're counting at 180 degrees. We're counting by pi radians, going back and forth on the x-axis. I suppose I should make a note that 0 degrees is 0 radians. It's hard to write this one because that 0 degrees looks like 0 to the 0, which is not equal to 0. It's undefined. Actually, it's indeterminate, excuse me. But we've got 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. It's just counting in 180 degrees. Any questions? How's everybody? You all right? Yeah. So think about going around in the circle. We want to start here at 0 degrees. 1 pi is at 180. 2 pi back to 3 is at 360. And then 3 pi, go around again. 4 pi, 5 pi, 6 pi. That's going to be our favorite because it counts like we normally count. We just count 1, 2, 3, 4, 5. We just say pi after each one. Next, we're going to start counting by fraction. Okay? Mentally prepare yourself for counting by fraction. And there's a lot of fraction haters in trig. And I don't know if I convert anybody, but let's see what happens. I'm going to take this 180 and we're going to cut it in half again. What's half of 180? 90. So 90 degrees. That means I got to take this pi and cut that in half. So what am I going to write? Pi over 2. 1/2 of pi, which I'm going to write pi over 2. So this 90 up here, that's a pi over 2. If we start counting in 90 degrees, we're going to be stopping at every axis. Here's going to be 0, 90, 180, 270, 360, 450, 540, 630. My processor is slowing down, and you can see it happen in real time. That's like the little swirly ball on my forehead, because adding 90 is hard, apparently. Now let's do the same thing. Remember, we're going to be stopping every 90 degrees, but we're going to think in terms of radians. 90 degrees is pi over 2 radians. We're going to start counting around the circle in multiples of pi over 2. So we're going to be 0. I got that one. Pi over 2. That's 1 pi over 2. Where's 2 pi over 2? 180. So this is 2 pi over 2. Now, we don't normally write it that way, but that's how it works. 1 pi over 2, 2 pi over 2. What's down here? 3 pi over 2. What's next? 4 pi over 2. 5 pi over 2, 6 pi over 2, 7 pi over 2, 8 pi over 2, 9 pi over 2, 10 pi over 2, and so on. When we see a denominator of pi, something over 2, we have pi over 2. That's our multiples of 90. 90 degrees is pi over 2. So if I give you 7 pi over 2, there's going to be 0, 1, 2, 3, 4, 5, 6, 7 pi over 2. Just like before, if we count around in pi, we don't have the over 2 part. It's going to simplify because I'm going to have 0 pi over 2, 2 pi over 2, 4 pi over 2, 6 pi over 2. And I'm also going to be able to cancel something out. So if you see something over 2, it's going to be one of these up here, 90 or 270. So we counted around by pi over 2. Okay. We're going to cut it in half again. We cut the 90 in half, and where do we end up? 45. Half of 90 is 45. And if we take pi over 2 and we want to cut this fraction in half, what are we going to have? Pi over 4. You cut a fraction in half, double the denominator. Pi over 2, if you have twice as many people, it's pi over 4 people. Fraction in half, double the denominator. 45 degrees is pi over 4. We can start counting around in pi over 4 and just stop at every multiple of 45 degrees, every multiple of pi over 4. Here's 1 pi over 4. Where's 2 pi over 4? Not quite. 2 pi over 4, if we simplify that fraction, it's going to be pi over 2, be at 90. 2 45s is equal to 90. So 1 pi over 4 is at 45. 2 pi over 4 is up at 90. What's the next 45 that we run into? 135. Now we're at 135, and how many pi over 4 is that? 3 pi over 4. What's the next multiple of 45? 180. And how many pi over 4 is that? 4 pi over 4. Normally, we don't write it that way. The 4's cancel, and we just call it pi. Where's the next pi over 4? 225, and how many pi over 4 is it? 5 pi over 4. Where's the next pi over 4? 270, because we're just going at an eighth of a circle. And so we'll get down to 6 pi over 4 for 6/8 of a circle. Normally we would call 6 pi over 4 3 pi over 2. One of the 2's cancels out. And the next pi over 4, 315. That's 7 pi over 4. And then 360 is going to be 8 pi over 4, otherwise known as 2 pi. So the over 4s that we need to recognize. When we see something, some fraction of pi over 4, some multiple of pi over 4, we're immediately thinking 45, 135, 225, 315. Those are the ones that are going to leave behind that 4 in the denominator. The other multiples of 45 at 90, 180, 270, and 360, those 4s get simplified. Any questions? Just counting by fraction. Doing carpentry in inches, right? And it's all those fractions. You have 132, then 232, but we normally just call that 1/16. Then 332s, then 4/16, which we call 1/4. So the counting looks really strange because we count 1 over 32, 1 over 16, 3 over 32, 1 over 4. And it really, when you start counting like that, it really starts to make sense why people don't like fractions. Any questions? How's everybody okay? Now we're going to grab the 30s and the 60s. For the 30s, I'm going to take my 90, I'm going to divide it by 3. So from 90, I'm going to branch off to make 30 degrees. So if I take the 90 and divide it by, I need to divide by 3 to get down to 30 degrees. How do I take pi over 2? What happens when I divide that by 3? There's going to be pi over 6. If I want to divide the fraction by, 3, I multiply the denominator by 3. So divide by 3, pi over 6. So now I have my radians for 30 degrees. A similar thing is going to happen. The 30, 150, 210, and 330, those are all the ones that are going to be left with a pi over 6. There's going to have a denominator of pi over 6. So if I give you one of these angles and the denominator is a 6, it's got to be one of these 4, 30, 150, 210, or 330. So 30 is where we have pi over 6. What's 2 times 30? 60. And so 2 times pi over 6. What's called 2 pi over 6? We've been counting by. So here's 30. 60 is 2 pi over 6. What's the more common name for 2 pi over 6? 1/3, pi over 3. We got pi over 3. 60 degrees is pi over 3 radians. So we're counting, let's count by 30s. And we're going to note 60 degrees is going to be pi over 3. So here's 130. 2 30s. Where's 3 30s? 90. And that'll be 3 pi over 6. Where's 4 pi over 6 going to be? 120. But what are we going to call 4 pi over 6? What do we get when we simplify that fraction? 2 pi over 3. So this 120, that's going to be, I have to do weird angles here. That's going to be 2 pi over 3. It's the common name, but will be also known as 4 pi over 6. Where's 5 pi over 6 going to be? 150. Think of the pi over 6 as 30. 150 is 5 times 30, so it's 5 times pi over 6. Where's 6 pi over 6? 180. And then 210 is going to be 7 pi over 6. What's the next, after 7 pi over 6? Where's 8 pi over 6? 240, but what are we going to call 8 pi over 6? Not 2 pi. So this is going to be 8 pi over 6, otherwise known as 4 pi over 3. Next up will be 9 pi over 6. 9 times 30 is 270. So down here, I'm going to put my 9 pi over 6. So if we simplify 9 pi over 6, we get 3 pi over 2. Ah, yes, right, because I have 1 pi over 3, 2 pi over 3. I didn't put the 3 pi over 3 here yet. So the next up is going to be the 300. That's going to be 10 pi over 6. But that's not the common name for 300 degrees. We can simplify that to 5 pi over 3. The next one is going to be 330 at 11 pi over 6. And then finally 12 pi over 6 back at the start. Starting to get messy now because we've counted around in all these different ways. But if we count by 30s, 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330, 360. Just replace the 30 with pi over 6, 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, and so on. Notice that there are only 4 that stayed pi over 6. 1 pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. So that pi over 6, and we have an integer times a pi over 6, that's telling us 30-degree reference angle. If we have an integer times pi over 4, that's telling us 45-degree reference angle. While we were going around with the 30s, we landed on all the 60s as well. I'm going to take the 180 and I'm going to get my 60 from this. If I divide 180 by 3, I'll be at 60. And if I divide pi by 3, I'll get pi over 3. We can also get there from taking the 30 degrees and multiplying by 2. 30 times 2 is 60 degrees. And 2 pi over 6 times 2 is pi over 3. Or we could take the 90 and do 2/3 of that, but no one ever wants to do that. Let's count around the circle in pi over 3, which is the counting around the circle in 60s. 160 is here in the first quadrant. 260s is 2 pi over 3. 360s is just 180. 4 pi over 3, or 4/60 is 240. 5/60 jumps over to the 300 for 5 pi over 3. And then finally, our 360 is also 2 pi, or 6 pi over 3. And we end up with this, and they're like, oh my God, this is such a mess. This was us counting around the unit circle to get practice counting by fractions. And to see how the unit circle is laid out, but we only need to remember the simplified versions, the ones that stick around. On the axis, we need to remember 2 pi is 360. Pi is 180. Those are the ones that stick around. Those are the ones we need to remember. On our y-axis, the ones that stick around are 3 pi over 2, or pi over 2 and 3 pi over 2. These are the names we need to remember. At the 45s, there are 4 that are sticking around, 1 in each quadrant. The names we need to know for 45, pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Going around in 60 degrees. Once again, notice that there are 4 with the pi over 4, 1 in each quadrant. The over 3s, there are 4 that stick around, 1 in each quadrant. Pi over 3. 2 pi over 3. 4 pi over 3. And 5 pi over 3. Those are the pi over 3s that stick around, 4 of them, 1 in each quadrant. And now the ones that simplified out, that keep a 6 after simplifying, there are 4 of them, 1 in each quadrant. Pi over 6. 5 pi over 6. 7 pi over 6. And 11 pi over 6. Counting around the circle makes more sense in degrees. 0, 30, 45, 60, 90, 120, 135, 150, 180. It's all going in one direction. The gaps are different because that's 45 degree angle. And it gets weird when we count around in fractions because we say 0 pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, pi. That is a weird way to count around the unit circle. So let's come at it from another way. Our 30-degree reference angles, pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6. Everything else, 1 through 12 pi over 6, will get simplified. I'm not going to write 3 pi over 6, because that simplifies to 1/2. I'm not going to write 8 pi over 6, that simplifies 4/3. 4/3 pi. So the over 6, those are our 30s. Our over 3s, those are our 60s. So I got 1 pi over 3, 2 pi over 3, 3 pi over 3 is the 180, 4 pi over 3, and 5 pi over 3. So the pi over 3s we need are 1, 2, 4, and 5. And the pi over 4s we need are 1, 3, 5, and 7. Everything else will be simplified. Now, You don't have to memorize all these values going around the unit circle, all these radiant measures going around the unit circle, but you do have to remember them. If that means that you sit down and memorize them, then so be it. If you just draw this unit circle with their degrees and their radian measures going around, then you will just start remembering them. Any questions? How's everybody? Everybody looks stunned because there's so many fractions on the board. Ah, so many fractions. I still don't like fractions, but I like 360 a lot more. $360 would be a better number of days in the year, especially if we're going to insist on like 12 months. Seven days a week really kind of messes things up, though. If we did 12 months, then we could have 30 days per month. And then each week would be 6 days, and that'll just be 5 of them. That'd be a little bit messed up, because if your birthday was on a Wednesday, your birthday will always be on a Wednesday. Maybe that's not. Incidentally, if we can't move the Earth closer to the sun to get 360, then I think it should be 360, and then there's 5 days that aren't on the calendar, and the whole world just takes 5 days off. I think that would be excellent. Any questions? You know, we can all agree to do that, right? Like this whole thing where we have to go to work at 8 o'clock in the morning. If we all collectively decide that we don't want to do that anymore, we can just decide that. We can just decide, no, we're not working at 8 o'clock. Whatever company you're working for, they can just decide that you're going to start later and finish sooner. And say, instead of starting at 8 and going till 5, you're going to start at 10 and just stop at 3. You can just decide that. Decide that. I don't think I will, so. I think of it like this, like suppose that this class, this is our company, and we need to produce 1,000 math problems. We need to do 1,000 math problems, right? And there are 40 of them. So it's like 1,000 divided by 40. How much is that? You don't need a calculator. There's a 0 in here. What's 1,000 over 40? What do we do with those zeros at the end? Get rid of it. Just divide by 10. So it's really 100 over 4. And how much is that? 25. Right. 25. Right. And let's suppose that just needs to happen. Now, the 25 per person, right? So the other thing that we have to think about is how often you have to produce those 1,000 items. Now, let's suppose that it takes all of us 8 hours a day, 5 days a week, just to get those 1,000 problems out. And that's too much, right? 8 hours a day is like 9 to 5. Everybody remember what 9 to 5 is? Life used to be like 9 to 5, but now it's like 8 to 5 because apparently, fuck you. But anyway, so 9 to 5, we're all working 8 hours a day. It's like, oh, you know what? We are still going to produce 1,000, but let's suppose instead of 40 people working on the problem, I get 80 people working on the problem. Now, how many are you doing? I've just taken your work and cut it in half. So with the same production level, we could just like work less per person and just have more people. We have more people, we can accomplish the same amount of work in less time, right? The population of the Earth has increased dramatically, and yet we're working more now. What did we do? How did we get to this point? Anyway. I'm not going to be allowed to run a company because I would just say, okay, there's 40 employees. The company produces $1,000 a day. So everybody gets 25 bucks a day, including me. I don't get more just because I own the company. Because we all own the company. So when there's profits, instead of me just keeping the profits, then we should all benefit from that, shouldn't we? Doesn't that make sense? Like profit sharing, isn't profit sharing a good idea? Should I not compensate you for your work? Or should I just buy another Lamborghini? I'm just kidding. I'm not going to buy another Lamborghini. I've already got 4. I got teacher money, man. Let's take a break. Here are radian measures. You have until the end of the break to memorize all these values, or just remember them. You don't have to memorize them.